Right. So today we're going to talk about how can knowledge graphs help make deep learning systems more interpretable and explainable. Manas is going to be our guest. He's a PhD student at the Artificial Intelligence Institute at the University of South Carolina. So Manas is actually in the final year as a PhD student. His dissertation is about knowledge-infused mining and learning. He is also a visiting researcher at the Alan Turing Institute. So thank you so much, Manas, for joining us.
Thank you, Walid, for having me.
No problem at all. I'm really excited to learn about this knowledge-infusing learning because I think it's more, it's very important to data labeling as well as model training afterwards. So without waiting longer, please go ahead and start the presentation.
Okay, thanks, Walid, for the introduction. So today's talk is actually structured around keeping knowledge graph as on the centric role of human AI collaboration. So when we say human AI collaboration, there's a lot of experience and detailing that human effort put into in annotation processes, and we want to see if there is a structure or a structured information can be constructed based on humans' experience and knowledge that can be incorporated into an artificial intelligence algorithm in a format in a different ways, I would say, so that it can the outcome that the model is generating can be reasoned on. So you can reason the outcome and understand whether the outcome is in the line of your thought process and the model is working in a way it was supposed to work. So today's talk is about knowledge-infused learning, and we will be talking about knowledge graphs for explainable AI. The outline of the talk, as I have constructed, is I will be giving a primer on the knowledge graph for the audience who are not familiar with the knowledge graph and how do they look like and how they have been constructed so far. I will be talking about knowledge-infused learning, giving up the more concrete definitions and details with some example use cases, and touching upon shallow infusion, semi-deep infusion, and deep infusion. Fourth point, I would be talking about knowledge-intensive language understanding. This is my current research goal and my current research focus, where I would be talking about developing novel task within natural language understanding, where knowledge graph plays a very critical role, and specifically the annotation efforts in this direction are immense. They are very much time consuming in my opinion, and how can knowledge graph supports those annotation efforts. In this entire presentation, I will be keep on talking about explainability and interpretability at its intersection with the knowledge-infused learning. So the last point of my outline is basically a mix of, it's kind of an assimilation across the different different paradigm that I'm talking about. So what does exactly a knowledge graph is? A knowledge graph is, in its a very simple definition, is a machine readable structured representation of knowledge that consists of entities, both entity and entity types, and they have relationships of various forms, and they can be stored as an RDF or a labeled property graph. Having an understanding of a knowledge graph, what exactly its utility in AI, we all know that the machine learning algorithms work on a very low level data sets. You have the data both in, let's say, numeric format as well as in the textual format in NLP. You pass it through a machine learning, which are very good experts in pattern recognition. They identify your patterns and they do a classification. Now, when you reason about this classification, that's where you get some importance score or probability scores for across all the features. Now, having an importance scores in front of you require the expert to go onto the resources separately and look for whether these features have some association, maybe a correlation or maybe a cause-effect relationship. If that exists, they say that, okay, then this feature importances are important and they make sense to us. What if we replace this process with the help of a knowledge graph? Knowledge graph have entities. They have connected relationships between the two entities. which are some sort of a rules, or they are some sort of a symbolic knowledge. And when you have this kind of a knowledge graph, you pair up with your deep learning or a machine learning architecture in various forms that I will be talking subsequently. But you assume this, that you can actually put them together. Then what you have to do is, the outcome that you're getting, you match it with the knowledge graph. If your connections that you are showing that these topics have some influence among each other, they would be connected by some relationship, direct or indirect relationship, single hop or a multi-hop relationships within the knowledge graph, and that would confirm that your importance scores are actually meaningful. Your identified features are important. Now, this is one process, but its implication is broad. Now your data is no longer irresponsible, but rather a responsible data, because it has been matched with the knowledge graph which has been constructed by an expert. And this forms a new paradigm which I have seen in various conferences people talking about, which is called as a responsible AI. There are various forms of knowledge graph that has been constructed so far. I would be talking about 3 specific which I know in my best of my knowledge. The first 3, A, B, and C, as you can see, are the manual effort knowledge graphs. The reason I'm saying it's a manual effort, because the annotators have developed some small instances of these structures, and then used natural language, then you have used artificial intelligence algorithm to expand on their structures to span onto a larger scale. Now, the very left, A, is an empathy ontology, which is a disaster ontology constructed using the FEMA archives. FEMA is the Federal Emergency Disaster Agencies. These people have a huge, humongous archives of recorded incidents and events that happens throughout the disaster. We took those and we constructed an ontology. We know that what are the concepts they are focusing on, which is documented in their archives. We know what are the relationships that they have been identified, that what are the causes. For example, that means when there is a hurricane, there is a power cut. So you have a causal association associated with it. People might lose the telecommunication. So that's again a relationship. So all those connected. Actually, yeah, Walid.
Sorry, I have a question. Like, how do you generate this data? Is this created automatically, like open relationships, or it is actually an expert labeling these relationships to create this ontology?
Yes, that's a good question, Walid. The FEMA archives are documented. I was not aware of it until as I just did a deep dive into the crisis informatics domain. When I got into understanding, the FEMA archives are very detailed record that every emergency responder note down after every incident. What are the activities that they have done? What are the incidents that took place? And what are the new incidents or new objects or new events that took place that they were not aware of? And this tells you that there are certain incidents that happens well before, and you can be well prepared. Now, coming to the construction, these archives are very much structured in their documentation. What I have done so far was to crawl these archives, get the data into textual format, perform a name entry recognition and noun phrase extraction and verb phrase extraction, and then use a similarity algorithm in a very simple case to figure out whether there is a connection between the two entities or not. Now, once you have constructed these entities, this constructs a knowledge graph. But when I give this graph to an annotator to look at this graph and tell me whether the annotation, whether the structure makes sense or not, then it becomes an ontology. So if there is an expert commitment into a knowledge graph, I would say then it is an ontology. If there is no commitment associated with it and it's just connection, then it's a knowledge graph.
Got it.
So similar to that, B is also a chem to bio to RDF, which is a very exciting ontology combining chemistry and biology together. It's constructed by and it's hosted at the Indiana University Bloomington. The third one is an atomic, which is a common sense repository constructed by Alan Institute of Artificial Intelligence. And they have actually constructed the ways in which a reaction or basically a communication can be interpreted. For example, if I say X is replying to B, then if I say X replies to Y, then X and Y communication can have various manifestation. So the various manifestation that you can have is represented in the C. So that whatever communication, whatever type of sentence, because every sentence that you pick is a communication. So whatever sentence you pick, it would definitely have a connection between the two entities talking to each other. So you can have different manifestation, different interpretation, but what would be the right interpretation is what common sense atomic would help you in. Likewise, for education, improving the learning outcomes of a student, you need a knowledge graph, because there are various terms and terminologies, and people read chapters through in an interconnected way, and there are various topics where you can stress on, and there are certain topics which you can lose, you can be or ease on. What are the important topics that you want to learn to excel in an exam, or what are the topics where you fall short, and what you want to learn can be actually be done using a knowledge graph. So that's a third. The D is basically an education knowledge graph constructed from the EPUBs from Amazon Books, and they are also being constructed from all other resources that are taught. So when I say resources, these are like books that are being taught in the high school as well as in the universities. The E graph is an automatic graph which is being constructed based on the series of tweets, the stream of tweets that the model is getting. Whenever a tweets are coming, the model only picks up the noun phrases and try to associate with each other. So whenever let's say there are 5 set of tweets, and after 5 tweets, let's say there are 1,000 tweets. From the 1,000 tweets, 10 are the events that were extracted based on the noun phrase and verb phrase, and then there is another 1,000 set of tweets coming after, let's say after a delay of let's say 1 minute or 2 minutes. You have another set of events. Now these two events might have some connection. So that connection is what this arrow is showing. That means as the events are progressing, more different versions of the tweets are coming with more variety of information, and they are connected with each other by this graph. Now you can actually look at this graph, and then you can annotate, you can evaluate, and you can even modify this graph.
So that was my question actually. How do you quantify the strength of this connection between events? You mentioned like if there's an event coming afterwards, maybe it's not related at all. Like how do you quantify that?
So right now, in the current state, what I have seen is people relying on the frequency of that occurrence of the event. If the frequency is very high, they have a very strong connection. If the frequency is low, probably it's kind of a coincidental.
So it's a co-occurrence analysis, basically.
Yes.
Okay, got it.
And the fifth one is an opioid drug knowledge graph, which is constructed based on the information provided in RxNorm, SNOMED CT, UMLS, and ICD-10. So these are like kind of a buzzwords, but let me just break down them. ICD-10 is an international classification of diseases. Everyone knows about it. It's a hierarchical structure, and it tells you about diseases, their severity, and what are the codes that are associated with it. We are not focusing on the codes. We are only focusing on the disease and their severity levels. RxNorm documents all the medicines, the drugs, and their side effects. And the third case, the UMLS, talks about gives the information of all the medical and the clinical terms, their definitions, and their association with other terms that are being documented in the medical vocabulary. Similarly to that, SNOMED CT, which is a systematized nomenclature of medicine, and CT is the clinical terms, is another graphical resource. So the person Kamdar et al. In the opioid drug knowledge graph he did was he brought these different varied sources together to construct a graph specifically only on the drugs. Now this is very interesting. When you have such a graph, you can understand black markets, you can understand the information about the drug. For example, the legalization of marijuana can be studied, right? You can also study about the various ways people do propagandas on Twitter about selling their own drugs. So there are a variety of problems in natural language processing which requires domain specific knowledge, and that's where such a graph plays a crucial role.
Makes sense. Great.
So moving further, having an understanding of what exactly knowledge graph is and what does it look like, let's just take an example of its explanation. How does a knowledge graph helps you in explanation? Suppose that you are as an annotator, you are getting a post from a social media profile where your eyes goes on to the statement that the person is having a depression because it's mentioning depression, but he also mentions that maniac episodes aren't the characteristics of depression. So there are two conflicting statements over here. And the task of the model, I'm talking about, like, let's say machine learning model, is to classify whether this person has a depression or he has an anxiety. A person knowledgeable of this very fact that depression has been talked about, but maniac episodes aren't characteristic of depression. We know that maniac episodes is the problem that the person is facing and not depression. So, and we know from our knowledge, let's say the annotator looks on the Wikipedia, figure out that anxiety is associated with maniac episodes. That means that the person is suffering from anxiety and not depression. He takes this post, does his annotation, and give a side note that anxiety has a manic episode. That's why I'm labeling it as a anxiety and not depression. Now that forms a whole bunch of important points regarding explanation. First, you know why a particular label was defined. You know the reason behind giving this particular labeling, and then you can take that whenever such a condition are happening, I can replicate the same information. So you can see that these are simple rules, but they are powerful rules in explanations. Now, how do we make it into a format that is understandable in terms of machine learning? Is that we pick entities. Let's say depression is one of are the most frequently occurring entities, and I say that manic episodes is another set of entity that can be extracted. Aren't characteristics is a negation, and among all the experiences that I have seen so far, I think regex is the best way of finding the negations. So I found regex as a best tool to identify the negation in the sentences. Now, if I have two entities and in which if there is a negation in the middle of the entity, I would definitely say that the first entity refutes the second entity. That means they do not have any connections. Now, I pick the manic episode and I might need to look at the knowledge graph to see manic episodes are attributes of what. And maybe I replace anxiety by depression, and then when I generate a representation of it, I make sure that anxiety comes up and the topmost probability in labeling the model. So certainly if I look at as if I put it anxiety over here, definitely the model will give, let's say, 51% of depression, 49% of anxiety. But there's a way that you can actually improve anxiety by looking at the other components, other set of factors within the text. But anxiety will still occur. But in this text, as it is, if you give it to a machine learning model, anxiety will not show up. So that's the power of having a knowledge graph, where you can not only identify the entities, but replace it with the entities that the classification is focusing on. If my classification was focusing on the attributes of the diseases and not the disease at large, then probably I could have focused only on manic episodes and not transforming it into another high-level entity.
So again, these entities are annotated manually, or do you apply an ER model to extract these entities as a first step? And then you try to find
these entities are already available. So
already anxiety has okay, so you have kind of a dictionary.
Absolutely, okay. absolutely.
Okay.
And since these information are very much documented by experts, right? So you have a confidence in the outcome that you're delivering. And the another important point that I want to make over here is that sometimes the context in which the information is being described might change, and that's why this knowledge graph comes very much in handy, because if the expert knowledge graph is not the context in which the post is being talking about, then you have the idea that at least this is not exactly the concept which I'm referring. For example, the person is feeling is getting panicky doesn't mean that he has anxiety. Unless he describes other conditions, other medical conditions that gets an equal hit on the knowledge graph, then only you will understand that this is actually a condition, medical condition. The not person is not mentioning anything in sarcasm or in other forms.
Okay.
So, having an understanding that we need knowledge infusion, we want to get more explanations from the AI. I relate very well that my thought relates very well with the Turing laureate Professor Leslie Valiant in his phenomenal paper in the AAAI 2006, where he specifically mentioned that the aim of the AI is to identify in the forthcoming eras is to identify a way of looking at and manipulating common sense knowledge that is consistent with and can support two fundamental aspects of the cognitive behavior, which is the ability to learn from experience and the ability to reason from what has been learned. So I think that is very much in line with the annotation process, Walid, I think, where the annotators where the annotators actually learn from their experience, and when they improve their annotation capability, the model needs to adapt to their changing abilities to annotate. So you are learning with your experience and you're improving with your experience. So therefore we are therefore seeking a semantics of knowledge that can computationally support the basic phenomena of intelligent behavior, which is artificial intelligence.
Yeah, I just want to say, like, the current models actually don't have infused knowledge, even though the labelers, they have the knowledge and they annotate. The model itself doesn't have that knowledge. It just understands the semantics, and that's where your work is very, very important here.
Absolutely, absolutely. So that's where we want to see that the way human adapts. I will give a very nice example subsequently as well. But the way human adapts, for example, the human information seeking behavior, for example, let's say a very simple case. People search online, they repeatedly change their query until they find the right information. Something very similar, model keeps on learning itself until it finds a series of information, of a good information. And that process of keep on improving itself is kind of like coming from experience. And that's where the human and AI teaming is very much important. And annotation efforts or annotation models are pretty much at the crux of human AI collaboration. Another interesting example that I have seen where we need infusion is coming from the empathy ontology and within the domain of crisis informatics, where you want to annotate emerging events. And when you annotate the emerging events, you not only, now assuming that you are annotating a text. When you're annotating a text is maybe like a few sentences. But if I can improve the text by adding some definition to those entities, I give the model a larger data set to train itself. So when it learns a particular label, it is not learning that particular label only by the entities in the text, but also by the definitions of those entities that
so for each entity, it has an attached kind of knowledge.
Absolutely.
So almost like an entity linking, but entity linking to a knowledge graph, I guess.
Absolutely valid. That's the right point.
Great.
And for this, I kind of used BabelNet. You can actually use any form of knowledge graph. The reason of using a BabelNet is only to gather senses. So that means I not only focus on the term waterborne diseases in the context of hurricane, I'm talking about waterborne diseases in general as well. So that the model knows that I should not only be focusing on the hurricane, but I should be also focusing on waterborne disease in other contexts as well, right? Because when I'm talking about crisis tweets comes in various contexts. They are not only focusing on if I have a stream of crisis tweets, it cannot tell me that all the tweets are in the same context of crisis. The person knows that the hurricane is happening, and within the hurricane, multiple events are evolving over the time, and they have multiple contexts. So that's why we need a definition as well, so that the model performs uniformly across variety of tweets. It's just like you read chapter 2 and then you come back to chapter 1 to understand chapter 2 a little bit better, right? So another interesting phenomenon that I found was when I'm understanding the emergency responders' behavior in addressing a phenomena, let's say hurricane, they kind of took some activities from earthquake as well. And this is because earthquake and hurricane have a parent entity known as a geological phenomena, and it has a series of activities being documented in FEMA, telling that these are the standard procedures that you need to perform. So that's why the person who was handling hurricane took some knowledge from the earthquake as well. So those are the interchangeable processes that comes in handy with the knowledge graph.
This is amazing. Like
Yeah.
this can be applied to multiple things. I come from a scientific background. I have a degree in physics, and actually subjects are kind of like if you have talking about chemistry or talking about physics, they are usually totally separated. But having actually a model that can infer different relationship between separate concepts, I think that's pretty interesting.
Absolutely, absolutely. And exactly that will be a certain thing that I would be talking about next as well. Okay. And I would be giving it as an open question, particularly to the annotation community, because that's itself I consider by myself as a challenging problem in natural language understanding. I will be coming back onto it subsequently, probably. If it's not covered, then I will definitely talk about it later as well. Another comprehensive example that I was able to relate with the knowledge graph was the comprehensive entity extraction from diverse knowledge sources. Now consider this small snippet of an article that I took from the news. You can see that different source of knowledge graphs, DBpedia and SNOMED-CT, have different forms of entities. And then there is a deep learning model, which is neural self-attention, being developed by University of California, Berkeley. It identifies certain set of entities, which is also important. But what is more important is the DBpedia and SNOMED entities, which are very much specific to coronavirus and CDC. So you see that diverse knowledge sources have a good manifestation in improving the capabilities of entity extraction. So when we are doing knowledge specific activities in natural language processing to improve natural language understanding, there are certain necessary properties that we need to be focused, we need to take care of. One of them, I don't want to go into too much of details of everything, but I would like to touch upon the measurement of biases. When we have when we create data sets, and data sets are given to annotators, and they are being given a task to annotate the data, they might get some guidelines, they may not get some guidelines, right? But those guidelines manifest those guidelines are representative of the data is not very clear to the annotators. Much of this thing goes into the annotators proclivity in getting a more understanding of the task and getting more details about the task, and by him sitting down and exploring and coming up with a good annotation processes. But certain things that I would like to touch upon is the historical, some of the set of biases that I found coming very much clear in some complex annotation efforts that have been done so far. One is the historical bias. For example, I gave a task for annotation on the data, and the person says, this is something very interesting. I have known this, I have seen this thing, let's say 5-10 years back. I take that 5-10 years data, old information, to annotate this current state, because I don't have the current information. The person has only given me the a particular post to annotate, and I don't know what's the history behind it. And I go through the history and does the annotation, and that's a bias, because you don't know how back in time you need to go to get the necessary information to get the annotation done. Representation bias is the person who is doing the annotation. It often happens that you annotate the same sentence, but it has been it has been written in a different way. You are annotating the same sentence again and again. So that comes into as a representation bias, because if you take those sentences as similar, your sample size is very small. You have no diversity in your samples. So that means you are only annotating one type of sample again and again. But they are just like, they are having one particular label to be very high and another label to be very low, right? This often happens in the annotation because English or the natural language is a very evilistic sentence. People do paraphrasing, people do rephrasing. They might use synonyms, antonyms, hyponyms, and all forms of variations in the language to make the sentence structure different. But when a person reads it, he reads and he gathers a semantic meaning to get the label done. That's it. On the semantic level, those two sentences are same. So your representation bias comes into the picture, because then you know that this is all like a biased sample.
Got it.
Measurement bias is another important point. Probably the name might not be appropriate, but let me give you the definition of it. When I say the person has addiction of drinking water, it should not be taken as a negative. Drinking water addiction means it's a good for a person. Right. But if I say the person has a alcoholic addiction, it has a negative consequence. So the two sentence, addiction is the same word being used in the two sentence, but one has a different manifestation than the other. So you cannot have one particular ruler to consider them as one sentence. You cannot make a label just because the presence of the addiction is there. The addiction in what context needs to be taken care of. And something similar is like a house arrest is different than arresting for a crime, and so on and so forth. Aggregation bias is a very known problem, and I think community in the AI have also highlighted that. So the aggregation bias is when you do some additive or arithmetic functions on your sentence, on your representation generation. Let's say I have 5 sentences. I generate representation of one, representation of second, representation of the third one, and do some convolution operation or dot product or some kind of mathematical operations to find a single representation, which might not be which might not preserve the semantics behind that sentence, and your annotation, your label is not the correct one which annotators have identified. So sometimes we call it like reading between the lines. That is what semantics is all about. You need to find the entities, find an association with the subsequent entities so that a trail can be constructed, and that should contribute to your label. Evaluation bias is another important phenomena, because sometimes so I would say evaluation bias and your representation bias go hand in hand. If your representation is problematic because of the distribution of the samples, evaluation will also have the similar problem, because now you will have the same one label kind of superseding the other label, and the second label never showed up in the in your high accuracy. Deployment bias again has a chain with representation and evaluation. Suppose you tested on let's say if you are making a model to identify whether the person has addiction or not, and you are deploying it the model into a concept where your system is actually experiencing those patients which are depressed or anxiety, maybe addiction never shows up. So your model will always throw no addiction, and without actually identifying the problem of anxiety or depression. So it's just like you are focusing your model only on the labels. As a consequence, the context that is there responsible for that label is gone. So that's where the deployment bias is a problem. And crime prediction models are the perfect examples where deployment bias have shown to be like visible to the end users.
Got it. So actually, for the crime prediction, do you know like in what context it has been deployed? This type of model?
Yeah. So the crime prediction, very interesting was this example of which I was talking about, the house arrest and arresting for the crime or addiction. He has a high addiction of, let's say, a very interesting example that I tested the model with was the person has a high addiction of curiosity. And the person has a high addiction for drinking alcohol, and I guess what, I get the same labels as an outcome. So that's a deployment bias, because a curiosity addiction is different than an addiction for an alcohol. So there are many examples like of this kind, and other examples are like addiction is alcoholic, like there's an alcohol addiction, and it has manifested in anxiety, depression, or suicide, or self-harm behavior, has some a chain. If your model is only focusing on the label of addiction, the deployment bias comes into the picture, because in addiction, in anxiety and depression, the model will not able to identify.
Got it. Yeah. So basically, in the training set, you're whenever there's a mention of addiction, probably it's like a bad thing with it. So the model will assume that whenever there's addiction, it's like associated to not a good thing.
Right.
And that's again, so it's an issue with the training data set is biased, kind of.
Yeah, absolutely.
It doesn't have good representation of real world problems.
Right. And sometimes a very simple case that I do to check deployment biases, I just extract the entities from the text and count the number of occurrences of the entities that are relevant to me. If that entity is very less in number compared to other superfluous entities being present in the text, definitely I want to restructure my data set before I can use a machine learning model. So I would rather sit and use a knowledge graph or kind of a Wikipedia or Wikidata to get more understanding of that entity and fill more information about that entity, so that entity comes into a majority illustration compared to be a low resource entity or a sparse entity in the data set. So the idea of knowledge infused learning is to develop a novel paradigm within the artificial intelligence. It's always within the AI that seeks to incorporate such semantics of knowledge that we talked about into a computational framework, so that the basic phenomena of intelligent behavior can be shown, which is getting a outcome which is the most intended way a model should work. Secondly, explaining the outcome so that I can understand the model is doing the way it should do. And the third point is the interpretability of the model. That means that once I know the behavior of the model, I can change the structure within the model by changing those parameters. Maybe not so when I say parameters, not like the hyperparameters. The parameters are the parameters where the knowledge is being added. So I'm talking about, let's say, rules or constraints or some thresholding values which are defined by experts specifically. So I want to change those parameters. So those are three things that are important and are very stitched together in knowledge infused learning. The three reasons which motivated me for knowledge infused learning was the domain specificity of the problem. Definitely, annotation doesn't happen for a generic language or a generic domain. Annotation happens for a very specific domain, maybe crime, for example, right? Crime prediction models. You can have a domain specific, let's say, it's of drug abuse. You can have a domain specificity in terms of harassment or cyber social harms, or you have annotation efforts in terms of hate speech, which are prominent in COVID-19 as well. These are domain specific problems and they are low resource. When I say low resource, it means that I do not have a large label data for these resources, and the annotation effort requires substantial amount of time, right? And the third thing is that these data sets, these problems, though they are low resource and very domain specific, there is some sort of definitions or some expert information that is being provided. Maybe psychologists or social scientists or cognitive behavior scientists have developed some kind of theories that we can actually leverage for making this for helping us or helping the annotators understand this data and get the correct annotation done, so that the models can take the right annotation along with the definitions, so that the both information that is being used to create the data is being incorporated into the AI model.
Got it. So the knowledge graph is actually embedded inside the neural network, basically, that you're trying to train.
Yes. Okay. So there are three ways in which this knowledge graph can be infused into the AI paradigm. The first one is a shallow infusion. When I say shallow infusion, it's about improving the data improving in terms of making it more semantic and conceptually correct before being passed into a machine learning model. The very simple example of doing this is whatever the features that, for example, let's say take an example of TF-IDF, right? A bag of words, right? Or bag of words means taking all the words in the text which are unique and those forms of features for your classification. What if I take a bag of words model, identify all my set of words that are there, unique words in the data set, and I replace those words with the concepts in a knowledge source. Now my importance scores are not on the words, but rather on the importance scores of the concepts that I can explain. I can show an example. I can illustrate an end user that these are the features that I found important, and these features you are very, very familiar with. Rather than the words where they have to struggle in making sense of those features, those words. The another point of shallow infusion is that it can reveal model sensitivity. For example, if the certain set of concepts, now I'm talking about concepts that are being contributing to the classification, if those concepts have very much codependency on the particular label as compared to other labels, that will actually be manifested in the model sensitivity. The model will keep on predicting one label and it will keep on ignoring the other labels. So you will figure out that there is some issues, or maybe there is a codependency or correlation between the features in the data set that were not visible with a bag of words, but now it is visible with a bag of concepts. So with a bag of concepts, I'm more explainable in my outcome in terms of my feature importance scores, or in terms of Shapley processes or LIME, which has been being used in explainability. If LIME is being tested on the bag of concepts rather than bag of words, it will do a good job than rather than running on a bag of words. So this actually motivated the construction of a generic architecture of shallow infusion. This architecture I'm showing is very much specific to natural language processing, where there is an input data and there is a phase extractor, a topic extractor, and then there is a simple matching function. In a very simple case, we assume this matching function to be a cosine similarity or a word mover distance, whatever mathematical function that we are thinking of. You do a matching between the phrases and the concepts in the knowledge sources, and you get a transform data. Now the transform data is the bag of concepts. Now when you're using that, you cannot generate representation of the concepts using a generic language model. You need to fine tune your generic language model to the domain, and it should be on using the same knowledge source. If you are using a lexicon as a knowledge source, that lexicon needs to be used for your fine tuning as well. If you're using a knowledge graph, you need to use a knowledge graph. So once you have these two structures, that's what you are integrating into the machine learning model. Now when I say these two arrows, the domain specific language model helps to generate representation of the concepts being identified in the transform data. When I say representation, it's a 300 dimension vector representation, or it can be a 50 dimension, or it can be 100 dimension. One interesting fact that I found was even the 10 or 20 dimension vector representation of a concept is sufficient to do a very good job in classification. So you do not need a very dense vector to do a classification when you are working on a bag of concepts. Now once you have done your model, you have your thetas, the model is trained. How well the model has learned the task, you can use Shapley plots on feature importances or dependencies. The Shapley plots are like very similar to LIME. They have the LIME is basically a local explanations, whereas Shape is kind of a representation through some heat maps on how these feature importances are varying across the samples. And it also allows you to choose that whether it is statistically significant in your classification. So you get the best of the both worlds with the Shapley plots.
Got it.
So let's just take an example of this shallow infusion in action. So suppose the task of a person or suppose the task of the annotator is to, given the two posts, one post coming from a support seeker and other coming from a support provider, whether this support provider is the right person for the support seeker or not. You are doing a very binary classification, but there's a lot going behind in your head. You're focusing on these highlighted areas. Oh, the person is talking about corona vaccines. He's talking about feeling alone, lonely, depression, trigger warnings, suicidality, and many more. So there are many cues being talked about in the support seeker. And you say that when I highlight the similar topics in your support provider, I could see that there's a match between what the support seeker is talking about and what the support provider is talking about. And maybe the support provider is a good one for the support seeker. I'm not sure about it, but based on this highlight, I would give a ballpark answer that this is a potential candidate to be the right support provider for the support seeker. When we look at the lexicon, now I have so far just highlighted the words. Now, if I use different source of information, I know WordNet talks about alone and lonely to be the one. I talked about suicidality, and we know that in the lexicon it also mentioned that suicide is an extreme condition in mental health. I know that lockdown and lonely are most commonly occurring terms in terms of COVID-19 context. And through the online, I know that for depression, people have suggested, like, it's kind of people also ask questions in Google. Like, you know that when I talked about how to cure my depression, people talk about go through a podcast, read books, or FaceTime with friends. So these are common examples. So you have a human annotation from there. Once you have this information, you know, yes, this support provider is the right support provider for the support seeker. So you got backing up your labeling with some kind of a background information. Now, what you have to do is that I have to either transform the support seeker post to a support provider's post based on these knowledge sources, or the other way around. You map your support provider post to the support seeker post, so that when you pass these two transform posts through a machine learning model using a language model, the representation preserves the context. Because if I pass this post independently as in its native form, the representation will be significantly different. As a result, the model will find a hard time in finding a convergence point, and it will probably label it as a 0, rather than giving it as a 1.
So the model here is trying to link the social provider to the social seeker, right?
Yeah.
Okay.
Yes.
So if there's a link, it's a 1. If there's no link, basically it's 0. Okay.
Yes. So we want to establish that link, and we want to establish that link using some source of information where I can find that manifestation. Right. Let's say I know extreme condition in mental health is suicide. So unless I have that documented evidence, I cannot do the transformation, because then it will not be an explainable outcome. It would rather be a heuristic, and which is not acceptable, and it might have a poor confidence.
Yeah.
So when we have this process, I was amazed to see that annotators also look at these set of features when they do the annotations. They look at events specific to the context. Let's say business closure, school closure within the COVID-19 context, which is called event-specific filters. They'll also look at the domain-specific filters, what exactly depression is, how a depression is manifested or expressed, how anxiety is being expressed. People also look at the syntactic features, which is, I would say, if an annotator has a very good background in English, he has a very good background in cognitive theories and psycholinguistics, then he might go into that details of the lower two section of features. But definitely the first two column are the features that a domain expert will definitely look at it. And as a consequence, this is if an end user is being shown such a graph which we generated computationally, that the support seeker was recommended SP1, SP2, and SP3 because of these set of features that we found to be important. That's where we say that this is an explainable outcome that we are getting from the knowledge-infused learning. One interesting point, Walid, I want to make it over here is that when we are giving as the outcome over here, we always give the section of the post in its native form and not the concept, because the person is reading the main post. However, but if he wants to get onto the more details, he can click on that post. It can drag you to the concept which was responsible for making this phrase or concept to be important.
Got it. So this is on the model prediction, or you're talking about just annotation at the beginning?
So this is specific to
the
your
outcome, you
model.
said.
This is the outcome.
So,
this is an outcomes. Okay. Yeah.
Cool.
So the annotation part is this previous part where you are transforming the text.
Right.
So so it's kind of like making a model where you pass this post, the model transform this post using the knowledge graph, and the annotators now just evaluate whether this annotation, this transformation makes sense or not. And if it does, then it says that, okay, you can pass it through a model, and the model generates this kind of a graph representation where the annotators again evaluate whether this understanding of the model is correct or not.
Great.
So we did this by making a small platform where we ask the users to ask a question, we get the recommendation, and the annotators evaluate whether these recommendations are making sense or not. And though we say that on an we get an approx 8.16 agreement from the 10 experts that we involved in this project, but as I said before, annotation is a very cumbersome and a time-consuming task, and it requires a lot of innovations in this process, right? So what I see is that this process can be scaled by if we have an AI-centric annotator platform, which can allow the annotators to look at the outcome, give a feedback, and the model retrain itself for a different outcome. Or it can be other possible that the annotators change the knowledge structure on knowledge source and and the model retrain itself on its new sources. Another form of knowledge infusion is the semideep, which is an extension of shallow infusion, which talks about more like a deeper and congruent incorporation. Like when I say deeper means now the model is, now I'm not working on the data, but rather I'm working on a matrix on which the model is basing its decision on. So over here, I'm talking about more of model interpretability. So the previous task of shallow infusion was focusing on explainability. The semi-deep infusion is on about model interpretability. When I say interpretability, it means that the models, as we all know, the machine learning models are driven by linear algebra. They have matrices. They compute matrices. They do factorization of the matrices. If these matrices are constructed not only on the input data, but rather at the intersection of the data and the knowledge graph, that's where the factorization might be very specific to the concepts in the knowledge graph and not on the data alone. So that's where we say it's model interpretable, because I know what's going inside the model. Let's take an example of it. So suppose you have a standard machine learning model. I have an input data and I have a knowledge source. I develop an attention weight matrix, which is nothing but a dot product between the concepts, representation of the concepts in the knowledge source, and the phrases or the noun phrases that I have extracted from the input data. I'm giving an example of a noun phrase and a verb phrase just pedagogically. You can actually expand it to many other parameters on many other phrases that are relevant to your task. Again, now you take a generic language model and you are fine-tuning this generic language model based on this matrix. When I'm fine-tuning it, that means it requires a matrix to find the important scores, and it tries to change its inner structure in a way that that the new representation are very closer to each other in this context, and if you remove this context, they are very far off. So once you have this, you have a domain-specific language model as a specific, and then you pass this matrix and this domain-specific model to your machine learning model for your prediction. Now, in this case, your data is still going into the model as it is. It is not changed. Domain-specific language model is required for the representation, and that the matrix now acts as an attention matrix in the model. It will allow you that only these specific terms within the text needs to be focused on, and rest of the words can be thrown out of it. So only the attention lies only on these terms that have a very high importance scores with the concepts, and only take those words representation from the domain specific language model. So don't take the representation from all the words, only take the representation of those words which are present in the domain specific language model.
Great.
Right? Let's me just give an example. Now take this post where there are some highlighted, as usual, highlighted terms which are important. A simple machine learning model gives a score of 0.71 and 0.29, yes and no. It is acceptable to some extent, but when we say why a model predicted a wrong label as at the very bottom, why when the actual label is depression, we don't have any question, because we will take these words, we'll start searching on the Google and figure out where these words are matched, which are the common behavior or common disease that this particular patient is manifesting. Now what we do is we look at the knowledge graph, we replace these terms by their parent entities. For example, bisexuality is a health related behavior, chaos in my relationship is also a health related behavior, and so on and so forth. Now as you can see, Walid, over here, the
so
variation,
you mask one word, I see. Yeah,
absolutely. Now with this, the variation in the text, the different terms and concepts that this text is happening is minimized, because now there is a common terminology being repeated again and again. Disturbance in thinking is occurring twice, and it is being occurring in association with obsessive compulsive disorder. So probably the person is having some personality disorder or obsessive compulsive disorder. Now what happens is that now you have a matrix that you can see on the left, which is being constructed from a DSM-5, which is the mental health knowledge graph. When I say knowledge graph, though in the practice we put it as a lexicon in the model, but it occurs as a knowledge graph because it exists as in a subject, predicate, and object. But in this task, we did not thought that relationship is important, so we kind of flattened it into a lexicon. We kind of construct this matrix, which is the concept, the terms in this graph, in the sentence, and the concepts association matrix. And when we tested with machine learning model, we get yes of 0.96 and a no of 0.04, which was remarkably well compared to 0.71 in the previous example. And when we tested it, we got the label as OCD because that's the true label that is getting. Mostly because it is occurring in majority, and someone with the blinds with a simple eyesight can say that it is OCD in this text. So that's an example of an interpretable and explainable learning going hand in hand in a semideep infusion. This is the example of how this mapping was happening, where we take the bisexuality has a code in the Snowbite CT, and then the chaos in relationship has another, sorry, the arrow went a little bit ahead. So it has another link of high risk bisexual behavior. Hope worthlessness is having is a level of mood, and you are talking about disturbance in thinking most often. And in this graph, I could see that disturbance in thinking is a symptom of obsessive compulsive personality disorder, and that's what actually manifests in your label as an outcome. Another important thing that I didn't do in this test, but it could be done, is to add the definition of OCD at the end. Is just like this current trend in the deep language model, Walid, where in order to generate a good response to a question, the paragraph and the question are being paired. So you pair your question to your paragraph to get a response generation. So something very similar, the power post and the definition is being paired to give a good sound label as an outcome. So it's kind of reasoning over the prediction. There's a capability of traceability. You can trace to because when I'm mapping it, I'm keeping the IDs, I'm keeping the definition. So I can trace back to the concepts and explain why particular label was given.
So question, if you go back, if you look at worthless, for example, it has been linked to feeling hopeless.
Yeah.
Is that the agreed upon definition, or depending on the context of worthless, it could be defined differently?
It could be defined differently.
So how would it know? How does it link to the correct definition, I guess? Does it look at the context of the word?
Yeah. Okay. Good question, Valid. So the worthless point in this context right now. So for example, let's say this research that I showed is on mental health communities on Reddit, right? It's on mental health communities in social media. So I know that in the mental health communities on the Reddit, they are very much bound by their rules, and it is very much preserved in the context. On the other hand, if I look at on the Twitter, this worthless might have different manifestation, might that has minus different context. Probably you might need to create specific lexicons or specific dictionaries to do that mapping, to train your model. But the interesting point is that when you are doing that kind of a transformation, it's always better to replace the term with its parent concept and try to assimilate across different posts, so that there is a uniformity across all your content, all your entities in your text, so that one entity is improved and the other entity doesn't improve. So when you look at the representation, they will be very far off.
Got it.
Right. So that's the whole point. Yeah, that's an important point. When you are talking about in a generic context, worthlessness have many manifestations.
Exactly. Yeah.
But if you're not talking about mental health, I'm talking about the level of mood.
Right. So this is like a domain-specific ontology kind of knowledge graph. Okay.
Another point over here is that when I talk about when you go up in the hierarchy, you're anyways going into a generic set. So irrespective of what context you're using, if I talk about, let's say, if worthless is not my point of contact, maybe I can take two hop of I can make a program where only those entities which are very much focused on my task, I can do it one hop traversal on that, and all the entities which are generic and they are not very much relevant to my context, I can do a two hop or a three hop traversal on that. So when I go onto the parent side, I'm kind of diverse, I'm kind of loosening my context. So whether worthlessness is talked in terms of OCD or not, it hardly matters to me. But I'm very much focusing on obsessive intrusive thoughts and need to get out of my head as the major phrases, because they will definitely occur very less in the context, and they form some major set of phrases or entities for our classification. Does it answer your question?
It does, yeah.
Yeah. Okay. So with this, we moved into the deep infusion part, where we are focusing on seamlessly integrating the knowledge into the deep learning paradigm. So there are various models that have been selected by me that would actually contribute in the deep knowledge infusion. This is a kind of the next inline force for the knowledge infused learning that I'm right now focused in. Among all the variations, I will be showing an example. So this example that you see in front of you is on the LSTM model, and how does the knowledge graph can be integrated. So what I have shown over here is that the knowledge graph in a BILSTM attention model has an attention matrix. Now, attention matrix, as you already know, is a kind of a square matrix. It's kind of the word by word attention. We want to improve the word by word attention with the KG based attention, where the KG is like the concept by concept map. And I want to do a KL divergence between them, because I want to say that the attention matrix that the model is learning is Q, which is an approximate representation of a true distribution P being defined by the KG. And you want to minimize the P and Q over the time, and that's where I show it as a KL divergence function. And you put them together as alpha times of the time when I take the KG representation, and 1 minus alpha time when I take the attention representation. So it's kind of a balancing between the two. I'll give you an example of that subsequently in the next slide. But what I have found is that in a deep infusion, attention metric is the most common area of infusing the knowledge graph. And mostly because attention is what is propagated up in the layers. And if you can fuse a knowledge graph or a knowledge representation, one of the questions that Walid you asked me was, what are the different types of knowledge graph embeddings? So there are various forms of knowledge graph embeddings. One is kind of like a geometric embedding, which is hyperbolic embeddings or point care embeddings. Other is like a distance measure based embeddings, which are transy, transH, and there are other embeddings which have a more complex function like wholly, or HOLE, or it can be, I have a RESCL is another representation, or it can be a deep learning based knowledge graph embedding, which is ConvKB, CONVKB. Irrespective of what representation you are picking up, the idea of not deep knowledge infusion is to allow the model make a conscious decision between when it has to preserve its attention function and when it takes to have to latch onto the KG. There's a past effort that one done by researchers in Carnegie Mellon, which talks about putting the entire knowledge graph into the deep learning model. That means if the hidden representation H dash significantly differs from the true representation in the knowledge graph, that time I will simply remove the knowledge graph and simply remove the attention representation and keep the only the KG representation. Whereas what I propose is that we do not simply throw out the attention representation, but rather keep its one component inside the model, so that when you backpropagate, there's a possibility that the concept, though it was very far off initially, might came closer subsequently. So that's why we always have a balance between like alpha times of A component plus 1 minus alpha times of B component, right? This is also a very standard procedure in a reinforcement learning paradigm as well, which is very helpful in annotation as well.
I guess maybe the risk of doing that, if it might learn like wrong concepts, because if they are far away from each other at the first layers, there is a reason like the other people, they removed it. But if you keep it, maybe it will learn something that's not representative in real life. I'm not sure if
Yes. There's a possibility. So what I did, what I have exercised into my capacity was to add constraints into the attention. Okay. I do not add the knowledge straight away. I will show you in the subsequent example. I did not add knowledge straight away, but rather I added knowledge as a constraint. So let me give you an example of that. Suppose this example is coming from a conversational artificial intelligence. I personally picked this because right now a lot of annotation efforts are going in conversational AI. People are actually developing novel data sets for conversational search, for conversational response generation, conversational question generation, and conversational information seeking. So this context is about conversational information seeking. Suppose, for example, you have a query, and the query has the term blockchain, relationships, cryptocurrency in it, and your model is generating a series of questions. If you can see that in a multi-round conversation process, the model ends up generating a question which is irrelevant to the user. As a consequence, this question is not accepted, and maybe subsequent question, if they are related to the previous, they might be irrelevant altogether. So and another thing is that when there's a multi-round conversation and the model is only focusing on a limited set of entities in the query, it will not able to get redundance. It will not able to get a diversity in the question generation. So what I found was, if I can develop a conversational information seeking agent that could explore the capabilities of a knowledge graph like this, so that it not only generates the questions, or not only generate a question based on the entities in the query, but also captures some of the related entities in the knowledge graph. I'm not going into the multiple hops or very in depth into the knowledge graph, but I'm only focusing on constructing a small graph based on the entities that are present in the query. So this agent is only generating a small graph. And when I looked at it, I could see that the model can generate specific queries to a more generic queries as well. So from generic queries to specific queries, it can go anywhere. And the reason is, a question on a blockchain is a generic query, and a question on a cryptocurrency is relatively more specific, whereas a question of Ethereum and Bitcoin is very specific question. So you go from a very high level to a problem focused question generation. Now, when you have this graph, when you have such a graph, how do you incorporate? So that's where the things becomes a little bit easy and straightforward. When I was looking at it, suppose you have a query. This is coming from let's say politics and policy background. You have a constituency parsing. you found all set of entities being present in the query using a simple NLP tool. What you have essentially done is that you take these entities and you parse it through a graph. Let's say I take a ConceptNet graph, you run your parser, your Pythonic parser, and you construct this small graph. Now, when you look at this graph, there are some entities and their attributes at the very end in the leaf. Now you traverse through these entities. You have various ways of traversal. You can do a depth first traversal, or you can do a breadth first traversal. It's up to the traversal strategy. You form different forms of triples. Let's say this is something small. Let's say I was able to retrieve 50 triples from this particular query. Now, once I have done that, I can have a kind of a BERT encoder or a, let's say, deep language model that could generate representation of these triples. I'm generating triples as a whole, not individual words. And I retrieve passages. Now you see the model is going through retrieving of passages based on the information in the triples. Of one of the passages that it has retrieved, it uses these passages. Now there are two encoders. One is a generic encoder over here, and so a generic encoder for the passages, and there is an encoder of the triples. Now you have two representations. Now what you have to do is that you keep on traversing this graph. You keep on getting more and more passages, more triples, more variety of passages. And this model has a, let's say you add it as a KPR, which I forgot to put a full form of it. It is knowledge aware passage retriever and ranker. So you retrieve the passage and you rank it. Once you're doing a ranking of these passages, you keep on retrieving it, you keep ranking it, and you pass it through an adversarial reinforcement learning paradigm on a model, which I will go in the detail next. That would take these triples, these passages, and keep on generating the questions. You keep on going in depth of your triples, you keep on getting more passages, and you're training your model again and again. Your model is getting new passages and new triples pairs, and it is generating more questions. And then you can subset this, or you can rank these questions based on their relevance to the user query. So those set of questions are there. So most important part is that with a deep infusion, you are able to bring entities which are not in the query to come in front of you in the questions, which are represented in the bold faced. Like national income, unemployment, which an annotator will know that this person might be interested in, but he has to sit down and annotate those questions. Here, the questions are coming in, and what you are essentially doing is that the annotator will have to evaluate whether it's a right question or it's a wrong question, or maybe he's been given a chance that he changed that question in a form that it is meaningfully correct.
Got it. Right. So it auto-generate kind of the question and the triplets.
Yes.
But then you still have the human who's gonna verify that auto-generation is correct.
Absolutely.
Okay. Got it.
So this process that's why I call it as a generative adversarial reinforcement learning, because adversarial means it checks whether it's a right or wrong with some minimal human effort. Reinforcement learning means it keeps on taking the knowledge source as an input and keep on changing its generation so that it can generate new questions over the time.
Got it. So I just have a quick question. Maybe I didn't get it. So for example, if you look at income, it branches to 3 different entities.
Right.
And from where did you get those? Were those from a different knowledge graph, or that's from the query?
That's only from the ConceptNet. So
ConceptNet, okay.
Yeah. If Walid, if you look at if you simply query conceptnet.io and type it income, it will give you national income, personal income, income tax as a related terms.
So the entities, I guess, sorry. So the entities that were extracted from the queries are the top 3 there: economy, inflation, and employment, right?
Yes.
And then you get the rest from the concept. Okay.
Yes. So I was able to see that. So in that ConceptNet has a very interesting thing. It not only allows you to go back, so not only go forward, but it also gives you one step backward as well. So you always have a parent entity being stitched together with your children entity. So when I looked at economy, inflation, and employment, I also found GDP. But when I looked at GDP has a link back to the economy. So I could associate GDP with economy in that point.
Yeah. Clear.
And the traversing I have shown in the red color is just an example of the way I generally follow a depth first traversal, because that way I can have a variety of triples being formed rather than doing a breadth first traversal. So it's up to the utility.
Okay, actually, just another question. How do you generate the questions? Because you have the passages and the triplets.
Yeah.
So you have some text generation that will generate the question out of the triplets.
Absolutely.
Okay,
Absolutely. So it's just
what do you use for text generation? What type of model?
Okay, so in this case, I use T5.
T5
for generation of the model. But the T5 configuration files, I made some significant changes in terms of the way the question needs to be generated and the format in which the question will be generated. So let me give you our details on that. So apart from this example of question generation, this agent that I was able to show you allows us to minimize some substantial annotation efforts, which are important in conversational tasks. You may know very well. One is the annotators search the web. They create good quality questions. They also shape the responses to those quality questions, and they maintain the information flow. They say that, okay, this is the first question, this is the second question to ask, this is the third question to ask. They maintain a process flow, and this is very much important. And doing this is a tremendous time-consuming effort. So we wanted to see that if this model, which we call it iSeek, which is information seeking question generation, can do this task very well, right? So this paper has been published, has been accepted in AAAI this year, and will be presented in February, I think on 24th, when the conference is happening.
Great, congratulations for that paper.
Thanks, Walid. There are two variants that we built in this model. The first variant is completely obsolete with the knowledge. Like, it doesn't have any information about the knowledge graph. It says that I have my query, I will do some question retrieval. I'm not focusing on my triple generation. I'm only focusing on the passage retrieved. The passages are retrieved based on the entities, and my questions are being generated. What I found was that in this case, all the questions that are very good quality questions, right, or we can say the questions which were generated based on the similar. So okay, the retrieving process of the passages, right? It's, as you can see the previous structure, it uses BERT encoder, and when we use a BERT encoder, implicitly cosine similarity or the similarity comes into the picture. When it happens, so even the entities which are similar to the entities in the query do show up in the outcome. They are corresponding to those entities, questions are generated, but they never make it to the top 5 or top K, because they were never in the point of focus. The point of focus were always the entities in the query. The triples, on the other hand, allows you to get that graph, that structure. If that structure happens, even the related entities are important to the query entities, which is nowhere you can enforce without using the knowledge graph, or somewhere, some form where the graph is happening. So what we did was we introduced a reverse cross entropy loss function, where we say that we put a threshold on the question generation. If the first question and the second question have a semantic relation with each other, being identified by the triples, then it is a non-adversary generation. But if there is no triples associated with it, if there is no connection between the first question and the next question, and they are just redundant or they are just random questions, they are adversary. Because whenever a person seeks information, it seeks a question in a flow. I would never generate a question if I'm learning to cook. I will not generate a question about fast food, right? If I'm learning about making a cuisine, I would rather know about ingredients, their quantity, their process, and how to cook the food, rather than looking for different types of fast food restaurants near me, or different types of fast food that are available. What are their calorie count is irrelevant to me for now. So those questions comes up when you retrieve the passages, because your retrieval of passages is completely driven by the entities, and the entities do not have relationship because you did not infuse the knowledge graph.
Okay, so you determine the relationship from the knowledge graph of these entities.
Absolutely.
And if there is
Absolutely.
zero connection, that means that's adversary
Generation.
Okay.
Yeah. So we introduce the reverse cross entropy loss, because reverse means cross entropy loss tells me that you move forward with the generation. That means these two are correct generation. So you're minimizing the error. But when you are having a right loss function, right? When you have a right prediction, the cross entropy loss is very low, right? That means that they are following up with each other. But if the model is generating a wrong generation, there's no way to penalize the model saying that this is a wrong generation, right? You cannot do a min max on the cross entropy loss. Either you minimize the cross entropy loss or you maximize it. So if you're minimizing it, the reverse of the cross entropy loss is what you have to maximize, right? So we introduce a reverse cross entropy loss to say that this is the adversary generation and this has to be minimized. Okay. So we minimize the reverse entropy loss based on the triple information. So there's another important point that we introduced over here was we use a pre-trained model Roberta, right? Which is, I would say, any pre-trained model is also a sort of a knowledge because they have been trained on some domain. I can take a pre-trained Roberta, fine tune it on a particular task and make it adapt to a particular task. So what we did was we took Roberta pre-trained model on a Stanford natural language inference dataset and tell that these two questions are entail of each other because this model is thinking so. So we just took Roberta as a way to generate probabilities so that our cross entropy loss and the reverse cross entropy loss function can work on it. So if you can see this thing, this is a deep infusion in terms of the constraints. I am putting a knowledge constraint on the deep infusion without making change in the attention matrix. So though we can do on the attention matrix, but this variant of deep infusion was only on the constraints. So when I ran the first variant of the model on this CAS19 dataset, which is a conversational assistance track dataset, which is KCAST. So we saw that what is interesting to note that you see that at 50,000 passages, 25,000 passages, of 10K, whatever number of passages, both the entities model and the entities with the knowledge graph model, the CNet KG, which is the concept net graph, have the same scores. They are not showing any improvement. That means that the role of the knowledge graph is not explored until it has been unless it has been involved in it in some kind of a constraint or some kind of a rules. The first type of model was simply driven by the entities in the query and did not explore the knowledge graph. So they never showed up. So even if you add the knowledge graph, the questions were never showed up in the top because they were never tested in the generation step. When I use the entailment constraint, we saw the improvement over here. What the important point that I want to sell over here is that there is a trade-off. The trade-off is that though in the initial epochs of my training, the entity only questions were generated all the way long. But when I extended the epochs to a little late, let's say 2 hours long, more training were done, the questions on the triple starts to show up in the top 5 or top 10. And that's because the model needs some training data initially to figure out what are your adversaries and what are your non-adversaries, and then picking up the non-adversaries and putting them into the correct samples. So it's just very simple how the annotation effort, right, goes invalid. You do some annotation and you give it to a machine learning model to learn from those annotations and then build upon the top of it. Something similar was happening over here. Initially, the model needs some kind of samples of adversary and non-adversary. Initially, the non-adversary were 0, adversary were all going up and up. But over the time, when the non-adversary sample starts to generate, they were put into the entailment constraint, and then the adversary starts to go down, and the non-adversary starts to come up. And that's where you get a variety or diversity in your question generation. So this actually concludes the the three phases of knowledge infusion, and what I wanted to leave the audience with a future direction that I'm very much excited, and I think that the natural language understanding has challenges along these lines, is how do you incorporate various forms of knowledge which annotators often see when they do the annotation process. First is the historical knowledge, right? When I say historical knowledge, it's a longitudinal information going back in time. For example, if I want to label a person having COVID-19, I want to look at his history. We always ask, we ask the question, have you been with a person in contact 14 days prior to your test? So 14 days is your history, right? Is a historical knowledge. Another is a planning and a process knowledge. Every annotation process has a strategy, has a process, has a planning. Whether if I'm annotating a particular, if I'm doing a multi-label classification, let's say a multi-label annotation, I will label 1 and then I will see again for the label 2, then I will see again for label 3. But for every label that I'm giving, the probabilities that I'm doing, I have to read through the task again and again. Right. I have to read through the passages. So that's basically, there's a planning and there's a process going on.
Yeah.
Right. Then there is a third is the analogy reasoning, where analogical data is to be constructed. For example, when you might know, Walid, since you have a background in physics, most of the classes that are being taught in physics, they are being taught with some analogy, right? You are being explained a concept by giving some analogical reference.
Exactly. Yeah.
Right. So we wanted to see that if the two data set, if there's a two text comes into the picture, can we say that the second is an analogy of the first? Does it appropriately explain it? Does it appropriately explain the first the data to be annotated? So we want to annotate the data to be annotated using an analogy. So we want to see that if this analogy has the same structure, if this data has the same structure, probably they are in the same context. So definitely that means that this concept can be explained with this another concept.
Got it. Right? So by structure, so what do you mean by structure here? If you can just clarify it.
Yeah. So by structure, I mean that, for example, let's say I do a constituency parsing, right? Say, which I did in the previous example. And I do a constituency parsing on the data to be annotated. I do a constituency parsing on the data that is coming from an analogy, right? Yeah. Let's say I'm explaining a chemical reaction using a musical chair. Right. I have two constituency parse tree. They have the same number of noun phrases. They have the same number of preposition phrase. They have the same number of verb phrase. Probably they are the same description of each other. So I can explain this concept with this analogy.
Got it. So it's purely based on the phrase structure.
Absolutely.
Okay. But that would be missing though concepts, because phrase alone is not I think capable of.
That's where the annotation efforts are important. Okay. And what I was dealing with was that you gave this to graph and you say these two are correct, and the annotators now annotate what are the concepts that are coming up, rather than they sit down and construct this graph and do the mapping, which is a computationally expensive task.
Got it.
So another example of a process knowledge is, in this case, is that suppose I want to classify a person as whether a person is having a suicide severity, suicidality or not. So what a clinician would do is that he goes through this flow chart, goes through individual questions, and then see that if the question number 1 is answered, question 2 is answered, but remaining questions are not answered, probably the person is having an ideation. If the question 3, 4 and 5 has also been answered, the person has still an ideation, but only if the person has answered the 6th question, then only I will give a behavior and attempt as a label. So there's a process in which this is being followed. Now, assuming this, there's a post that is being given to you, and you are being asked to label it as one of the suicide severity labels. And you have been given this flowchart. The annotator will look at this flowchart, look at these questions in the questionnaire, and will label it whether the person is right or will have a label of ideation, behavior, or attempt, whatever the appropriate label is. Now we assume that we take this graph. We want the model to take this graph and the data and annotate it and give us the label. And the annotator sees that, whether this annotation is right or wrong. And what are the points where the model went wrong. And that's where the feedback, the reinforcement learning comes into the picture.
Got it.
So this is just another example of the same process. The person is talking about feeling nervous, anxious on the edge, and you forms a series of questions. You go with yes and no, whether he's actually having that condition, what is the degree of frequency, then causes, then remedies, and so on and so forth. So if you have this structure, then your question generation process or the annotation process becomes more streamlined. And you are saying that now in this process, annotators take a whole lot of time, and they have a whole lot of job that they have to sacrifice the time and effort to do such kind of annotations. We want to see that if an expert knowledge source like a questionnaire can help us in doing this same structure. So this paper is right now under review at ACL, and we are hoping to have a good feedback from the reviewing.
Great.
Subsequently, like this is an explanation of how this process happens, that you have a question, yes and no, frequency, causes and remedy. Once yes and no has been identified, you go into the frequency. Once frequency is defined, you go into the causes, and so on and so forth. So now assuming this, like the way I'm seeing it working in annotation, Walid, is that you have a text coming in. You first pick whether it's actually a relevant post or not. Then you check at the number of times the entities that are relevant to you are present or not. Third thing, you check whether there's a cause related phrase being present in that sentence or not. And the fourth thing is that you check whether there's a remedy being present or not. If the person has mentioned all of these things, definitely it is a true post, right? So you are actually if you look at this is actually a process an annotator would follow. And you want that process to be followed by a model, so that the annotators does an evaluation.
Yeah. So this is not like assisting the annotator, but more you embed it in the model, like inside the model.
Yes, absolutely.
Okay. And how do you convert this to actually an algorithm that can be used inside the model?
Absolutely. So what we do is that we kind of make it as a search procedure.
Okay.
Like kind of search process. So search procedure is that first we want to search whether yes and no is possible in that, right? If the yes and no is there, that means there is the person is looking for some help, right? The person is looking for some advice. So yes and no is about that. The third is that the frequency and the degree of the condition. That means how many times the entities is being present, that is being often looked at it. Then the third thing is that whether there's a causes being present or not. So what your model is doing is that your model is generating questions for itself in the backend, and is filling up the probabilities for those values, whether it is 0.8 and above or it is less than some threshold. And over the time, it's saying that at the end that the person is having a condition and he has shown causes and remedies, and we consider the person with this particular condition. So that is the label that you're giving to the person. And then this whole chain that you can see is explainable, because now the annotators can see this coming in in front of them, and they can say why the particular model has given the particular label.
Got it. So the model will generate all these processes.
Absolutely.
And then the label will verify. Yeah. Okay.
I don't want to go into the algorithmic details of it, but I would sum it to a short that it uses A* search and deep language model to generate questions for the deep language model, A* search to pick whether the next question is the right question to be asked, given that the previous question has been answered correctly. So it's just to maintain the flow. So A* search allows you to maintain the flow.
Got it.
So this is the entire structure that is being given to annotators, and the annotators say whether it's yes or no, and they say that no, the order is not right. And so this was a first in line study that we conducted. So definitely the annotator says the order is not correct. So it's whole change that you are doing. But you see what I'm doing over here, Walid, is that I'm asking them only to do the annotation, binary and ranking, rather than giving them to sit down and generate these questions.
Right. Yeah. So these are auto-generated by the model and they just verify.
Yes.
Yeah. Makes it
For example, let's say, do you have problems getting to sleep? Do you have problems staying asleep? I know some of these questions are similar. Redundancy is definitely there, but to an extent it minimizes the annotation effort. Like if you sit on, you can scratch these questions. Let's say saying that these questions are not relevant, you can remove it. But
binary decisions are always like the easiest in terms of annotations, for sure.
Absolutely. So yeah, that's the open-ended questions that I have wanted to look into the natural language understanding. And these are the references of some of the works that I have published in knowledge-infused learning, some of the works that I have done in mental health care, crisis informatics, and conversational AI, all at the intersection of human and AI collaboration. All of them work focuses on explainable AI. And my next step and my future research is only in towards developing more specific and more scalable deep knowledge infusion models.
Got it. Great. That was the presentation, or you have more?
Yeah, that was the presentation.
That was perfect. Thank you so much. So I guess the next question is, this is like a very fascinating research, to be honest, because it touches many things, right? It touches from explainability to improving even the models themselves. So it's getting closer to how human thinks. Think about real world concepts. So how soon are we at applying these knowledge graph infused models in real world applications? Are we still far away? What are the challenges to make them in production, as opposed to staying in research?
Absolutely. So that's an absolutely good question. And I have if you have asked me this question last year, probably I would not have a concrete answer to it. But today I do have a concrete answer, because the work that I did on a deep infusion, the the information seeking question generation model, is looking forward towards for a patent with a company. And it has been I'm for with respect to NDA, I close the more details, but it has shown to be generating questions that are beyond ground truth questions. So the quality of the questions were beyond the human level performance. And in some cases, the annotators have suggested that the system I seek was able to generate better, or have a much better generated questions when we did a blind human evaluation.
Oh, that's amazing! So it's actually getting better than experts in this case.
Yeah. Wow. But I would say that to some extent, the experts also raise a point that some of the questions are less useful. Some of the questions they were saying that to some extent they can change it. The questions are good. Like they have to do a minimal effort in doing the annotation task,
labeling.
The labeling task. And that was the beautiful response that I've ever got from 30 different annotators.
Oh, wow.
When they were given, let's say they were given, I think, 100 some queries across mental health, public policy, politics, legal news in general, sports, and geography. So a very diverse domain was given, and I think we really got a good consensus from the annotators.
So diverse domains, but different model for each domain, right? Not the same.
Same model. Same model.
Okay.
Same generic model. Only the knowledge graph that was given to the.
That's what I'm saying. So the knowledge graph is specific to those domains.
Yes.
Okay. Got it. No, this is amazing. Actually, I have one last question. Is the comparison of this model, knowledge infused model, with these huge GPT models, and these models don't have any knowledge, I think, infused in that side.
Yes.
So do you see that these models are going to hit the limit, that they cannot improve any further, and it requires infusion at the time, or by just increasing the number of parameters going to billions and billions, you think eventually it will be able to get better and better? Will there be a plateau, basically, in the performance?
I would not refute saying that if you keep on training GPT-3
adding more parameters,
on multiple parameters, it might do a good job subsequently. But the question here is that on its adoption in real world practice.
Exactly,
For example, if I talk about a healthcare, let's say, and it gives you a correct prediction, and you say, yeah, it's an amazing prediction and it's right. Let me just reason it why this particular prediction is happening, and the model gives you 2,000 words that it found important.
Exactly. Yeah.
Now you have to sit down and see of those 2,000 words were actually contributed to your classification. And you figure out that the words which are important to your classification has a minuscule probability, right? And they just came here by coincidence probably, because the model was capturing the huge turf,
Right.
and it gave you a particular label.
Got it.
And another point is that when I'm talking about using these models on edge computing, right?
Yeah, they're huge, right?
Yes. You cannot fix them into a mobile devices.
Yep.
You need a small model for your mobile devices. In that case, I have seen a recent research by of one of my colleague who graduated with the Ph.D, Kalpa Gunaratna, who showed that with a small BERT, they could do much better than a large BERT on a small devices, right? And they were able to showcase a particular strategy in which these models needs to be aligned, and how OCR and BERT can be put together in a nice way of doing it on the mobile devices. But but most importantly, he showed that large models are not always the go-to options in doing some recognition or an object detection. It's just like you are pushing one nail into the board by using a bigger hammer, or a machine mechanistic hammer, which might not be needed at that point. So that's my response to the use of deep language models.
Right. And I think this is, I mean, your work will be actually very important for getting almost this very high performance with a smaller data set where you can, and that's where the problem is, right? Like a lot of businesses don't have labeled data set, and even if they have, it's very small. So infusing this with knowledge graph, I think it's going to open up like a whole new era.
Absolutely. Like for example, like a very simple case is that you get the annotated data to annotation, right? You use that data. You say that these are the knowledge graph I think that are very much important. These are the set of pages that are important, and I give it back to the person who gave us the data. I would not refute saying that if you keep on training GPT-3
adding more parameters,
on a multiple parameters, it might do a good job subsequently. But the question here is that on its adoption in real world practice. For example, if I talk about a healthcare, let's say, and it gives you a correct prediction, and you say, yeah, it's an amazing prediction and it's right. Let me just reason it why this particular prediction is happening, and the model gives you 2,000 words that it found important. Now you have to sit down and see of those 2,000 words were actually contributed to your classification. And you figure out that the words which are important to your classification has a minuscule probability, right? And they just came here by coincidence probably, because the model was capturing the huge turf, and it gave you a particular label. And another point is that when I'm talking about using these models on edge computing, right?
Yeah, they're huge, right?
Yes. You cannot fix them into a mobile devices. You need a small model for your mobile devices. In that case, I have seen a recent research by of one of my colleague who graduated with the Ph.D, Kalpa Gunaratna, who showed that with a small BERT, they could do much better than a large BERT on a small devices, right? And they were able to showcase a particular strategy in which these models needs to be aligned, and how OCR and BERT can be put together in a nice way of doing it on the mobile devices. But but most importantly, he showed that large models are not always the go-to options in doing some recognition or an object detection. It's just like you are pushing one nail into the board by using a bigger hammer, or a machine mechanistic hammer, which might not be needed at that point. So that's my response to the use of deep language models.
Right. And I think this is, I mean, your work will be actually very important for getting almost this very high performance with a smaller data set where you can, and that's where the problem is, right? Like a lot of businesses don't have labeled data set, and even if they have, it's very small. So infusing this with knowledge graph, I think it's going to open up like a whole new era.
Absolutely. Like for example, like a very simple case is that you get the annotated data to annotation, right? You use that data. You say that these are the knowledge graph I think that are very much important. These are the set of pages that are important, and I give it back to the person who gave us the data to see that whether this set of information are relevant to your data set, and they say, yeah, these are the relevant documents. Then you take that document, you construct a knowledge graph, and starts to improve your annotation process.
Got it. Yeah. Great. Perfect. I think we're a little bit ahead of time. Okay. Thank you so much, Manas. It was very, very insightful.
Thank you, Walid, so much for those questions. And so some of those questions were really, really on the point, and I really appreciate that. And they actually made this presentation much more detailed.
For sure, yeah. Like we need to have interactive discussion because
absolutely
that's how the audience will learn more. And I think, we definitely learned a lot. Like this is very, very fascinating. Thank you so much. I'm really looking forward for your next step. So you're finishing up your PhD this year.
Yes. Yeah.
Looking forward for your contribution and
definitely always. I will definitely share with you and will keep you in the loop. If you are still seeing my screen, the second paper in line from the top is a new problem that I didn't discuss in this presentation. It's about solving math word problems, and it's a next challenging problem in natural language understanding. And to my experience, a lot of annotation efforts are going on in this area, and there is only one data set that has a good quality. No other data sets are there in solving the math word problems.
Got it. Great. Thank you so much, Manas, again. And hopefully we'll have you again.
Thank you so much.
When you go to your next venture.
Thanks, Walid.
Thank you.
Bye.